All right, here's our next problem. This is the escape velocity equation. So let's go over this real quickly. It's the square root of 2 times big G. I've given us big G over here. It's always the same number. It's called the universal gravitational constant, 6.67 times 10 to the minus 11th. It does have units, but as long as everything else is in the proper units, you're good to go. All right, so we have the velocity, the escape velocity, which is going to it's going to be in meters per second, is equal to 2 times big G times m divided. M is the mass of the object you're trying to escape, and r is the size of, r is really the distance that you are from the center of that object. Okay, so let's take we're given some values for Earth. There's the mass of Earth. So m has to be in kilograms, and r has to be in meters. Notice it's given to us in r here is given to us in kilometers, which is often the case. All right, so what we're going to do is so the first thing is we're going to figure out the escape velocity from the Earth. All right, so Earth. From the surface of the Earth. Let's understand that. All right, we're going to use the numbers. The only thing is, right, r here, the radius of the Earth. So that's why it's the surface of the Earth. If we were leaving, the Earth from the top of some mountain or something like that, we would have to include then what you do is you say r is equal to the radius of the Earth plus whatever the height is. All right, so that's the way that you would do that. We're since it's from the ground, the height is 0. Okay, everybody understand that? So in this particular case, the height is 0. All right, so now r has to be in meters. So it's so this is the average radius of the Earth, 6,400 kilometers, and of course we know that's an m. Sorry, we know that 1 kilometer is 1,000 meters. It's a simple way of doing it, or 10 to the third. This is another way of doing it. So the kilometers cancel, and so this becomes, so you could say, 6.4 times 10 to the 6th. That's perfectly fine. Or you could say 6,400,000. Either way is perfectly fine. I like scientific notation. So 6.4, you can see there's 3 zeros here and then 3 zeros right here. So it's going to be 6.4 times 10 to the 6th meters. All right, so that is going to be used right here. All right, so that's the way that we do this. All right, so the escape velocity. So we can 60. Here, I'm gonna. So we know the mass of the Earth. Let's see if I can squeeze this in here. So it's going to be the square root of big G, which of course is 6.67. I'll use the E minus 11th. Remember, that means the same thing as times 10 to the minus 11th. And then times, oops, 2, I forgot the 2. Right, so 2 times that. Yeah, this is getting too messy. And then times the mass of the Earth, which is 6 times 10. See, it's so much easier to just use the E rather than the times 10 to the 24th. But that means the same thing. And then divided by this, which is 6.4 times 10 to the 6th. All right, so here. Anyhow, I'm gonna redraw that, so it looks a little bit better. All right, so let's, I rewrote it. So remember, this is the escape velocity from the surface of the Earth. All right, so It's always, the square root of 2g, the mass of the object that you're trying to escape, and then the distance from the center, the distance that, whatever's trying to escape is from the center. So because you're on the surface of the Earth, we worked out and of course, R has to be in meters, M has to be in kilograms. Right? So this is the mass of the Earth, 6 times 10 to the 24th. This is the radius of the Earth. It's 6,400 kilometers, or 6.4 times 10 to the 6th meters. That's what you want to use to do this particular problem. And then, of course, big G is what it always is, and there's the 2. All right, so let's work this out. Here, let's get our scientific calculator. Move that over just a little bit. All right, so it's going to be, here, let's clear all that. All right, so it's going to be 2, I'm going to do everything underneath the radical first. 2 times 6.67, oops, I messed that up. 6.67 times 10 to the minus 11th times, all right, so that's 2 times that, and then times the mass of the Earth, which is 6 times 10 to the 24th kilograms, divided by the radius of the Earth, which is 6.4 times 10 to the 6th. All right, so remember, this is everything underneath the square root. All right, so that's the answer, and then we take the square root of that answer. All right, so the square root turns out to be, let's write this down. So it's 11,183. I mean, we're gonna round it to one place past the decimal, and we're gonna convert it to kilograms. I'm sorry, kilometers per second, because that's the typical value that we'll use. All right. So anyhow, so this is 11. So here, let's write it down. 11,183. Okay. So this is 11,183 meters per second. And then, of course, we say, well, in 1 kilometer, there are 1,000 meters. All right, so the meters cancel. And so that, to change this, we just need to move the decimal point 3 places to the left. All right, so this becomes, so if I round it, it's 11.2, right? So 11.2 kilometers per second. All right, so that's actually the escape velocity from the planet Earth. This is an enormous velocity. Let me just let's make sure that we all understand that. And in fact, okay, let's do a quick conversion just to show you what a large velocity this is. So I'm going to convert it to miles per second. Let's do that right now. So it's roughly 11.2 kilometers per second. I'm going to write it this way, and you'll see why in just a second. And so I know that in 1 mile, remember, we reserve lowercase m for meters. So in 1 mile, there are 1.6 kilometers. All right. So now the seconds don't change. So now that's going. Once I take this 11.2 and divide by 1.6. All right. So let's get my calculator here. All right, let me clear this. All right, so I'm just going to use 11.2. 11.2 divided by 1.6, that is about 7, right? So that's how fast if you're going to launch a rocket and it's never going to come back to Earth, it should be moving at about 7 miles per second. Miles per second. All right, so let's continue converting this. And let's suppose that we convert seconds into minutes. All right, so we know that there are, of course, 60 seconds in 1 minute. Notice I'm using MIN for minute. Of course, there are 60 minutes in 1 hour. So basically, if I so look, the seconds cancel, the minutes cancel, and so if I were to multiply this 7 by 60 squared, right, then I would have the answer in notice miles per hour, right? So there's the miles. There's the hours, right? That's the only two. That's the only units that haven't canceled. Right, so 7 times, so you could just do 60 squared, right, times 60 squared. So that's really 7 times 3,600. And so that's going to give us more than, I've done this many, many times. It's going to be more than 25,000 miles per hour. All right, so rounding it here, this is about. So this is and we don't normally change stuff to miles per hour. It's more for a comparison, right? So this is about 25,200 miles per hour, right? Miles per hour. I put an S on there. All right, so that's the escape velocity from the surface of the planet Earth. I mean, that is, think about it, right? Maybe you're driving in a car, and that car, the average car, let's say in the United States, could get up to about 100 miles per hour. NASCAR cars can travel at a little more than 200 miles per hour. This is 25,000 miles per hour. Jet airplanes will travel close to 600 miles per hour. The speed of sound is about 700 miles per hour. So this is an enormous velocity, and of course you need a rocket, right? This is why the age of space exploration, to send stuff into space it requires a rocket, real major technology to be able to achieve this velocity. Of course, you don't have to achieve the velocity all at once. You can gradually reach it, just like rockets do. But by the time that the rocket leaves the planet Earth, it had to have reached this velocity. This is the minimal velocity to leave the Earth and never come back. That's what we mean by the escape velocity. All right. Let's do the orbital velocity real quick. Since we already have all the numbers in here, if I just simply the orbital velocity is a reminder. You don't include the 2. All right. The square root of 2. All right. So here, let's figure that out. All right. So I've written the orbital velocity. We don't include the square root of 2. So this number is going to be smaller, right? This is definitely smaller. All right, so we'll put the numbers in and figure this out. All right, so I've rewritten this. I've done the calculation over here on my calculator. So it's 7,907.7 in meters per second, and then of course you divide by 1,000 to convert it into so it's just under 8 kilometers per second. Okay, so that's the orbital speed. That's like, for example, the speed at which satellites travel, including the International Space Station. And as a reminder, I put down what we'd already calculated. The escape velocity in kilometers per second is 11.2. So the orbital speed is always less, right? Because you don't have that factor of a square root of 2 in there. Anyhow, this is the escape velocity. This is